Good evening, everybody. Today we are going to be tackling a different subject that I do not do and have not done previously in these videos. That being, today I want to do physics as opposed to just pure mathematics. Say, way physics is sort of applied mathematics, so close enough. And it is my actual favorite subject here. And today I want to discuss the implications of the acceleration due to gravity, but not only that, the idea of why do we consider the acceleration due to gravity to be well, constant. Like, so basically, we're told very often that we're basically told commonly that the acceleration of gravity is a constant and does not change. But this could actually be. But today I want to explore this. Test it through something very simple. And to do this, I will be using the first of all Newton's universal law of gravitation. What we see here is the law being that F of g, the force of gravity, is equal to the universal gravitational constant, I'll explain it in a second, times the mass of object 1. In this case, we'll say we have an 80 kilogram man, times the mass of object 2. The mass of object 2, in this case, is going to be the Earth. And basically, I'm going to note this saying ME is going to be equal to 5.972 times 10 to the 24th kilograms. And then we have our r squared. That's going to be the distance between the center of gravities of the two objects. And the center of gravity of Earth, and basically the center of gravity of Earth is located at the center of the Earth. Therefore, we say here that our center of our value is going to be 6.378 times 10 to the 8th meter, or 10 to the 6th meters, I'm sorry. So, what can we do with all this? Well, first of all, I want to first take a moment to really pick apart the universal gravitational equation quickly. So, what is it actually saying to us? We can ignore G for now, and just focus in on our first two. We have the mass of object 1. Basically, this equation is telling us that as the masses of our two objects increase, the gravity will proportionally increase. Well, as the distance between our two objects increases, the gravity, but the attractive force between these two objects will actually decrease, would decrease squared. It's essentially we're applying the inverse squared law to multiplying the two masses of the objects together. Inverse squared law being a law, or an inverse squared law according to Kepler's laws. Should specify. Now then, if we actually multiply this out, we can find out that, now then, when we actually do some multiplication, we can say here that this is actually going to be equal to a kilogram times a kilogram, or a kilogram squared, over meter times a meter, or a meter squared. But in reality, that's not actually a force unit. A force unit, or otherwise known as a Newton, is going to be equal to our kilograms times the second squared divided by meters. So then how exactly do we, how exactly do we make kg squared over m squared equal kilogram second squared over meters? Simple. We add the universal gravitational constant, which when you multiply this number, which has units, newtons meters squared per kilogram squared, we will essentially, the meters squared and kilograms squared will cancel out, and you'll be left with newtons. And this value right here is also something that you need to do to balance the f of g. We determined this through Newton's second law, that the force exerted upon an object is going to be equal to that object's mass times the acceleration at which it went off it when the force was applied. So why did I set up all this? Well, I thought, what better way to do this than to try to make an example of trying to figure out. Let's figure out our acceleration due to gravity through Newton's second law by first figuring out, let me write this g back here, the force of gravity through the universal law of gravitation. So, let's quickly do this down here. In order to this for now. Notice the value for now. So, first off, we're going to say here that our force of gravity is equal to the mass of object 1, say 80 kilograms, times the mass of object 2, 5.972 times 10 to the 24th kilograms divided by 6.3781 times 10 to the 6th meters, all that squared. So when we do this, you can do it on a calculator if you so choose to determine it. You can find out here that you actually get to that the gravitational force applied upon the object is going to equal approximately 7,838.498 newtons of force. Okay, interesting. Or, sorry, I thought that's a future example. Sorry, the decimal point should be here. But so, interesting. But what's the point? Why need this number? Well, we can actually plug this into Newton's second law. Our force of gravity is going to be equal to, we're going to set it to the 80 kilograms as the mass for this equation, because this equation, the Newton's second law, is primarily describing the acceleration of our object, the object itself. So the force of gravity, before wondering, the force of gravity is the attractive force between two objects, meaning that yes, you pull the Earth towards you, and the Earth pulls you down towards it. I'll get to why one of those forces is significantly that, yes, then yeah, you might be familiar with Newton's third law and stuff. But now we're going to essentially say here that the mass is going to be 80 kilograms in this instance. So we have our mass is going to be 80 kilograms times g. When you divide out, you get the g is going to be equal to 9.79 meters per second squared. But most people who take a physics class would say, okay, that's pretty close, but isn't g supposed to be equal to 9.81 meters per second squared? The answer is yes. The reason why this number is going to be off from that value is that really the 9.81 is 1, an estimate, and 2, notice how the equation specifies the distance, the r squared value as the distance between the two centers of gravity. If I were to stand on the top of a skyscraper, technically I would be further away from the center of gravity of the Earth. Therefore, the r squared value would increase, thereby meaning that, technically speaking, when you are on top of a skyscraper, your acceleration due to gravity is actually different. Same way as if I went into a mine shaft, the acceleration due to gravity is actually going to be greater when I'm deep in a mine shaft. And you also have other moments here. And then let me direct you to a little diagram up here of the Earth. Some people might notice here that the Earth is weirdly shaped here, and it's not just because I'm terrible at art, but also because the Earth, this is exaggerated, but the Earth is actually thicker near the equator. This is because of the Earth's rotation, and essentially, when this thickness means that the r value here is greater than the r value near the poles. So you see here that the r value in itself is an estimate, and that causes the 9.81 value is also an estimate of the values on the surface of the Earth. That's going to be primarily where our sources of error are come from here. This is primarily going to be where our sources of error come from. And so then, now that we kind of established this much, we can actually kind of figure out here, then you might actually be able to figure, so you might be asking yourselves a question now. Okay then, now that I know this, now that I'm aware of this new phenomena, your next question is going to be, okay then, so why is it going to be constant though? I mean, like, why is averaging it acceptable? I mean, like, and the answer is, well, for one, you kind of just saw that 9.79 isn't that far off from 9.81, and why is it okay to average it together anyways? For one, it's the same reason why we're not using air resistance, because air resistance, yeah, everything is impacted by air resistance on Earth, but the truth is, nobody really has the time in high school, and nobody really wants to, in high school at least, solve out for air resistance and that would be, well, not advanced necessarily. it could potentially overcomplicate the matter when ultimately it's just not a big enough deal. Same thing of why we're using the average acceleration due to gravity is because the changes in it are just not big enough to really be significant. But now I can also present you with the other reason of why exactly are we that does this mean that the thing of saying that the acceleration due to gravity is constant is wrong? The answer is yes and no. It is wrong in the way that it is not always constant, as you can manipulate it, as I said, by increasing your or decreasing your distance to the center of the Earth. But it is, but then you could make the argument that it is going to be independent. Primarily speaking, it will be independent of of the mass of a person. Why is this? So let's change f of g to some absurd value. Let's change the kilograms. Say we want to change them to 80 kilograms to 100,000 kilograms. So it's 100. 1, 2, 3. Let's write this down here. Is going to now equal 100,000 kilograms times. I'm just going to say me this time. Oh yes, obviously you got to multiply this also got to multiply by g times g over, we're going to say our value, r squared. So basically we can take that, then we're going to multiply it by our me, which is going to be 5.972 times 10 to the 24th, divided by the 6.378 times 10 to the 6th, whole squared, times 6.67403 or 430 e to the negative 11th. A little syntax error. Let me just see here for a second here. Where would a sorry, got a little syntax error there. Give me a second here. Okay, let me just say 6 point. Sorry, we typed it in wrong. Calculator error. My fault. Yes. So basically, we're gonna get ourselves our f of g this time equaling about 979,812. Then divide that by 100,000 kilograms. And then when you divide it by 100,000 kilograms, you're going to get the g still equaling 9.798. It's going to be very similar to, or with an estimation, it's going to be 9.8. So, what just happened? Why isn't it changing that as much? Shouldn't it be changing more? The answer is, what's happening here is as we increase the mass of one object, the force of gravity increases. And so because the force of gravity, and then as the force of gravity increases, the force of gravity and mass are increasing at the same rate. But that means that the acceleration due to gravity, doesn't really need to change to account for this. Thereby meaning that our acceleration due to gravity, you can easily say that the acceleration due to gravity is independent of mass for the most part. There's obviously going to be you can obviously apply a lot of different exceptions here, like things to do with density and lift force, but those are really not to do with acceleration due to gravity. So the answer to the question of, is acceleration due to gravity always constant? No, because of distance, because of how not only how you can manipulate your own distance, of how the distance between you and the center of the Earth is going to change anyways, because of how the Earth is shaped and how it's not a perfect sphere. But you can say that it is equal, that the acceleration due to gravity is independent of the mass of the object, thereby keeping the whole bowling ball falling at the same rate of a feather idea true. So I hope this video, you found it informative. I hope to see you next time.